So our section 6.1 is highlighting once again our greatest common factor and factor by grouping. Our learning objectives are being able to find the GCF of two or more expressions, and then also being able to factor out that greatest common factor from whether it's a monomial, binomial, trinomial, any polynomial. And then the last thing is really learning how to factor by grouping, which is a method that will pop up a lot on either quizzes or assessments in this class, as well as in pre-calculus and calculus. You have to take those classes later on. Let's start with a warm-up. These 3 warm-up questions. The first one is just being able to factor 56 into primes. So think of, okay, what is our prime factorization? And so we ask ourselves, what are 2 factors, aka a factor pair of 56? And could be anything. We know 2 goes in. Do we know if a higher number goes into 56? And if so, what? Well, yeah, we have 2 and 28. We could have done 4 and 14. We could have done 7 and 8. Doesn't matter. The numbers that you choose sort of determine how many steps it's going to take. So I'm actually going to put in both options here. Let's say we chose 7 and 8. You'll notice that we'll have less steps there. But we'll start with the 2 and 28. 2 is prime, so we'll circle that because we're done on that left-hand side. And then we have to keep going for 28. We can break that up into 2 and 14. Once again, 2 is prime. 14 can be broken up into 2 and 7, and 2 and 7 are both prime. So if we wanted to write this in terms of primes, we would simply have 2 times 2 times 2, also known as 2 to the 3rd power, times our 7. Now, if we looked at 56 and we pulled out 7 and 8 straight off the bat, we know 7 is prime. 8 can be broken up into 2 and 4. 2 is prime. And then 4 can be broken up into 2 and 2. So technically, it actually took the same number of steps. We once again get 2 to the 3rd times 7. And we're done. Question 2 asks us to find the least common multiple, aka our least common denominator. Use cake method. Really highlight this.
Hi.
It's okay.
How are you?
Oh, I'm good. How are you?
How was the feet?
It's much better. Thank you. Yeah. Have a good one. So we have 18 and 24. And so we want to ask ourselves, what is a factor that goes into both 18 and 24? 6 goes in. How many times does 6 go into 18? How many times does 6 go into 24? And then we ask ourselves, okay, 3 and 4, are these numbers relatively prime? The only factor that is shared between the 2 numbers is 1? Yes or no? Yes, which means 3 and 4 are relatively prime, which means our cake is done. And so our least common multiple is just the product of that sort of boot. So our LCM, which is again the same as our LCD, is just 6 times 3 times 4, which gives us 72. And then they didn't ask us for this, but the GCF between these two numbers is just the diagonal part where we only have one number here, which means our GCF is 6. But sometimes they have more than one, and you would just take the product of the diagonal. And then finally, we have question 3, where we're just asked to multiply these two expressions. And so we're going to utilize our knowledge of distributive property, our famous property. And so we get negative 3a times 7a gives us negative 21a to the second power, right? Using our rules of exponents, same base, add the exponents, 1 plus 1 is 2. And then negative 3a times 8b gives you a negative 24ab. We're done. So these were sort of, oops, go back. These were our 3 warm-up problems before jumping in. Okay. So we have a little notes page. Maybe I'll have a student read this for me. Usmain, do you want to read this for me? I don't think she's paying attention. Usmain, you want to read this? And then project your voice so we could all hear.
Start with the product and then break it down into factors, splitting the product into factors is called factoring.
Beautiful. Thank you so much. And so what we've done for the past few weeks is we've been utilizing FOIL, right? We've been expanding out binomials. We've been expanding out the product of a binomial and a trinomial, or a polynomial and another polynomial. Now we're reverse engineering that. Now we have this expanded form and we want to factor it. So if we have this expanded form, we want to figure out how do we factor it into our 2x times x plus 3. Right, we have another little notes page. Maybe I'll have Jose, I'll have you read the yellow, and then Anthony, I will have you read the blue. Jose, you want to read the yellow for me? No, not at all. All right, darling, do you think you can read it for me? Thanks.
Of 2 or more numbers. Now we will factor expressions and find the greatest common factor of 2 or more expressions. The method we use is similar to what we use to find the LCM.
Thank you. And then greatest common factor? Anthony, right? Alexander. I keep confusing your name. All right, Alexander, can you read this for me? Thank you.
Greatest common factor theta of 2 or more expressions is the largest expression. That is the factor of all 3 expressions.
Great, thank you so much. So yeah, this is our formal definition of our GCF, but I think at this point in the course, you know how to find the GCF, as well as our LCM, aka our LCD. Remember, LCM and LCD are the same thing. Why do we have these 2 different names for it? Well, usually we refer to LCD when we're dealing with like adding and subtracting fractions. Right? LCM is more of the general term. What is our least common multiple between these two different numbers or three different numbers? And then below here is just the step-by-step procedure in finding a greatest common factor. This is more the traditional method of going about it, but honestly, if you just use the cake method, you'll never get it wrong. It's very straightforward, direct, and systematic. Okay, so let's jump into our example 1 for today's lesson. And we're asked to find the GCF between these three terms. And so how do we go about doing this? Again, let's write out the three terms. And we're going to go ahead and draw out our first layer of cake. Now, I personally like to take care of the coefficients first. And then once I have the coefficients out of the way, then I can deal with the variables. So we ask ourselves, with greatest common factor, we actually need to figure out, okay, what's a factor that goes into all three of these? So what's the number that sort of pops out besides 1? 3, exactly. And so when we pull out 3, how many times does 3 go into 21? Yep. How many times does 3 go into 9? And how many times does 3 go into 15? Good. And then we ask ourselves again, is there a GCF that we can pull out of 7, 3, and 5? No. So we're done with the coefficients, but now let's look at our variables. And with the variables, all you have to do, really don't have to do much work here. You just want to look for the variable that has the highest or that has the lowest exponent. So out of 3, 2, and 1, which one's the smallest? That x to the first power, which means we're going to pull out that x to the first. And how many times does x go into x to the third? Yeah, so we have 7x squared. What about our next one? 3x, and then our last one? It's just 5. Great. And so now our cake is complete, right? We have our nice little candles. And so in order to find the GCF, it's the product of our diagonal. 3 times x, which gives us 3x. And we're done. Hey, good morning. We have another little notes page. Let's see. Edith, I'll have you read this part for me.
Something useful to represent a number as a product of factors. For example, 12 as 2 times 6 or 3 times 4. In algebra, it can also be useful to represent a polynomial in factor form. We will start with a product such as 3x squared plus 15x and end with its factors. 3x
Yep, in
minus
parentheses, yeah.
x plus 5. To do this, we apply the distributive property in reverse.
Beautiful. Just like I said, we're reverse engineering everything. And I'll actually write that down. We are reverse engineering. we're going from expanded form to factored form. Versus what we did before, was factored form into expanded form using our distributive property. One of the famous methods with distributive property was our FOIL. But if we were dealing with the product of trinomials, then it was just our generic distributive property. And that's why we once again highlight our formal definition of distributive property down here. Right? How do we go from our factored form to our expanded form? Well, we utilize distributive property, but now you're given your expanded form and we're going into factored form. You're pulling out a GCF in order to get that fully factored form. We are reverse engineering everything. And so these are, once again, our formal steps in pulling out a GCF from a polynomial. I break it up into those two different parts. I first find the GCF of the coefficients of each term, and then I look at the variables and pull out that lowest exponent from each of the variables. So now let's take a look at our example 2. We are asked to factor this trinomial. So first, can we pull out a GCF? Yes, we can. What do we notice each of these terms share? And if you don't see it straight off the bat, again, off to the side, write your cake method. Once you get the hang of it, you don't have to do cake method every time. But cake method sort of gets you sort of in the habit of what we're looking for. What's a factor that we can pull out of 8, 12, and 20? Yeah, and when we pull out 4, we're left with 2m cubed minus, good, 3m squared n, and then 5, right? mn squared. And so now we can clearly see 2, -3, and 5 are relatively prime. So let's go straight to the variables. What's the lowest exponent for our m? It's just m, right? And then do we notice, like, do we have any n, or do we have at least one n in each situation? We don't have it here. So we finished up our cake, which means what's our GCF? The product of 4 and m, which is 4m. So now let's pull that out. And when we pull that out, what are we left with? Well, lucky for us, we just did our cake method, which means we're just left with what we have in purple over here.
No.
Hmm?
The
Oh, I didn't pull it out yet. You're right. Thank you. I should have written it down over here. When we pull out the m, what are we left with? 2m squared minus 3 mn, and then plus 5n squared. That and bring it over. And what operation is between that negative 3mn and the 5n squared? It's just a plus. All right. So we factored this out by pulling out a greatest common factor. You think we can factor it a bit more? We're back to our whole AC method, dealing with trinomials. What's our A here? Our C is 5, right? Well, actually, our C is not just 5. Our C is 5n squared. So the product of this is 10n squared. And then what's our B value? Think back to our general equation of any quadratic, right? Ax squared plus bx plus c. But in this case, our x is really an m. So we have am squared plus bm plus c. So we're treating that n value as a constant, which means our b value is what? Negative 3n. Okay, what are factor pairs of 10n squared that add up to negative 3n? And if it's still a little iffy, write it off to the side and just look at the coefficients first. What are factor pairs of 10? And then we'll worry about the whole n squared in a moment. You don't have to worry about any negatives right now. We'll put that in a moment. All of our factor pairs of 10 are just 1, 10, 2, and 5. Now, of these two, if we manipulate it with a negative symbol, can we get negative 3? Yeah, right? That second one, positive 2 and a negative 5 add up to negative 3. All right, we're almost there because now we have to incorporate this whole n squared. And so again, factor pairs of 10n squared that add up to negative 3n, which means, do you think the n squared is going to stay together, or do you think we have to break it up into like an n and an n? If we kept it together, we're going to end up with n squared when we take the sum. And we notice that when we take the sum, we don't have an n squared, we just have an n. And that's why we have to break it up into n and n. So now let's just double check to see if this is correct. 2n minus 5n, does that give us negative 3n? It does. And then 2n times negative 5n, does that give us a positive 10n squared? Actually, it doesn't. Actually, did I mess up with an operation somewhere? Yeah. It doesn't. So what does this tell us? Is it factorable? No. Yeah, so this is our fully factored form. Can even highlight that this part here. What is this known as? A blank trinomial. Any questions on this page? Yeah. Let's do another example together. Again, GCF. Look at the coefficients first. What can we pull out very easily? A 5. Then we're left with x to the third and negative 5x squared. Now let's look at the variables. What can we pull out? X squared, right? The lowest exponent. So now we're left with x and negative 5. And are we done? Yep. Which tells us what's our GCF? 5x squared. And so when we pull that 5x squared out, what's left in the parentheses? Yeah, x minus 5, which is, if we did everything correctly, that's that last layer of our cake. And then we're done. We can't factor that any further. Questions on this at all? How are you guys feeling? Scale of 1 to 5, 5 being getting the hang of it, 1 being I'm so lost. Let's give this a shot. Once again, see if you can pull out a greatest common factor first before jumping into our special factoring abilities. Look at the coefficients. Can we pull out a GCF between 8, negative 10, and 12? Good. We pull out 2, and we're left with 4x to the third y minus 5x squared y squared. And then we have this plus, you can keep the operations in, that won't affect anything, plus 6x y to the third. Now that the coefficients are relatively prime to one another, let's just focus on the variables. With x, what's the lowest exponent? It's just our x to the first. And then with y, what's our lowest one? It's just y. So when we pull that out, we're left with 4x squared minus 5xy plus 6y squared. Which means when we pull out xy from the trinomial, we're left with that last layer of cake. We'll just copy and paste over. And then it's a very similar situation to that first example, but we need to run through it to make sure that our trinomial is not prime. So let's once again utilize our whole AC method. What's our product of our A and our C? 4 times 6y squared gives us 24y squared. And then what's our B? Negative 5y. What are factor pairs of 24y squared that add up to negative 5? So again, let's just start off with factor pairs of 24. One, 24, 2, 12, 3, 8, 4, and 6. And of these 4 factor pairs, do any of them add up to negative 5?
3 and
3 and negative 8. But we want to ask ourselves again, if we utilize 3 and negative 8, will that give us the product of positive 24y squared? No, it won't, right? So what can be said about this trinomial? Yeah, it's a prime trinomial. Which actually in most cases, it's not the case. You will be able to factor it out. I think they're just trying to give you some examples of prime trinomials as we're building up our skills. We're just focusing on pulling out that greatest common factor. Say that again? Oh, yes. Yeah, I forgot that too. Thank you so much. Yeah, our GCF is the product of that whole diagonal. Good catch, Jazala. Yeah, so this is our final result.
C for B, when you factor it, does it matter that it's negative 5y? Can it be negative 5xy?
Very, very good question. It can't be negative 5xy because remember, we're looking at the general equation of a quadratic in this case, ax squared plus bx plus c. And in this case, we have our ax squared here, and then our bx, this is our bx. If we take out the x, then our b is our negative 5y. Does that make sense? The variable that we're utilizing as our general equation is our x. And then our constant includes that variable, 6y squared. Just like we did earlier, I think this was an example 2. We were dealing with m's and n's. And so instead of looking at our general equation ax squared plus bx plus c, we were looking at now, okay, what is that x instead? Okay, we're going to make that x our m. So we're looking at am squared plus bm plus c. And so our a in our am squared is 2. Our b in our bm, well, there's an m here. We're going to cross that out. So our b is negative 3n. And then our c, our constant, is this whole thing, 5m squared. Makes more sense? Yeah. I know, they try to trick you on problems like that. And I'll write that down over here. So our let our a be equal to 4x squared. Our b is equal to negative 5y. And our c is equal to our 6y squared. Our a is just that 4. It's not 4x squared. So example 5, I'll read this part. When the leading coefficient is negative, we want to factor out that negative as part of the GCF. That way, if we don't have that prime trinomial and we're able to factor it, it makes it a little bit more easier for us. So now let's take a look at this example, negative 4a cubed plus 36a squared minus 8a. Pull out a greatest common factor. Well, between negative 4, positive 36, and negative 8, what's a factor that can be pulled out of all three? And remember, we want to pull out that negative, right? So let's pull out a negative 4, right? And when we do that, we're left with a cubed minus now 9a squared. And then plus 2a. Now let's look at that variable. What can we pull out? Just an a. So that we're left with a squared minus 9a plus 2. And so what's our GCF here? Negative 4a. So when we rewrite this, we have negative 4a, and then in parentheses, our whole a squared minus 9a plus 2, which does this happen to once again be a prime trinomial? Yes. Right. Can't find any factor pairs of 2 that add up to negative 9. Prime. Yeah. Any questions at all? We're going to move on to our example 6. This one's a fun one, right? Because remember, greatest common factor. What's something that they both share? Does anyone see it? They both share this binomial y plus 7. We really don't even have to do a cake method here. We can just pull that out straight from the start. This is sort of like the preview to factor by grouping. And then when we pull that out, what are we left with? A 3y minus 4. And then we're done. So now we're finally onto that third bullet in our objective, which is factor by grouping. And so let's see, Herlinda, maybe I'll have you read this for me.
Sometimes there is no common factor all the terms of a polynomial. When there are 4 terms, we separate the polynomial into 2 parts with 2 terms in each part. Then look for the GCF in each part. If the polynomial can be factored, we will find the common factor emerges from both parts. Not all polynomials can be factored, just like some numbers are prime. Some polynomials are prime.
Nice, thank you. And we've really sort of practiced our prime polynomials a lot in class today, with almost all of our examples being prime, or having part of the results being prime polynomials. And so this page is just the formal step-by-step procedure in factor by grouping, but we'll really take our first example of factor by grouping nice and slowly so that you can really see it from a concrete example. So let's take a look at our example 7. And so we want to factor this by grouping. Anytime you're factoring by grouping, you're sort of looking at those first 2 terms and seeing, okay, what's the greatest common factor? I can pull from that. And then looking at those last 2 terms and what's the greatest common factor? I can pull from that. And so in our yellow scenario, what can we pull out between xy and 3y? They both share a y, which means what's left in parentheses? Just x plus 3. Now, if we do this correctly, you will notice that what we have inside the parentheses should be the same. So now let's pull out a greatest common factor between 2x and 6. And when we do, what do we end up with? 2, and what's left in parentheses? X plus 3. What do you know? They're the same. So now we can pull out that x plus 3 from each of these terms. And then when we do, what are we left with? Y plus 2. And we're done. We just factored this polynomial by grouping. And if you're not convinced that what we have boxed is the same as what we started with, you can check by FOIL. So we have x times y gives you your xy. We have x times 2 gives you that plus 2y. We have 3 times y gives you the plus 3y. And then we have 3 times 2 gives you the plus 6. And so is this the same as this? It is indeed. They're all being added to one another, so moving terms around does not change the result. I think I put in a 2y somewhere when it should have been a 2x. X times 2 is 2x, not 2y. But yes, you can move things around utilizing your commutative property, and you'll notice that what we started with is the same as what we get by using FOIL. Let's try another few examples together. So we have a part A and a part B. We're once again practicing this whole concept of factor by grouping, but we'll go a little faster this time. So what's a GCF between x squared and 3x? X, which means what's left in parentheses. Once again, that x plus 3. What's a GCF between negative 2x and negative 6? Pull out that negative. Negative 2. What's left in parentheses? X plus 3. Did we do it correctly? We did indeed. What we have in parentheses is exactly the same, so we can pull that out. And when we pull out that x plus 3, what are we left with? This whole x minus 2. And we're done. look at part B. So first two terms, what can we pull out? A 3x, what's left in parentheses? 2x minus 1. Last two terms, what can we pull out? A -2. What's left in parentheses? 2x plus 1. Did we do this correctly? We did indeed, because what we have in the parentheses is exactly the same. So now we can pull out 2x minus 1 from each term. And then what are we left with? 3x minus 2. And we're done. Questions at all? Yeah. Did I?
Enough.
Yeah. Let me see. Did I make a mistake? -4x. This should be a minus, right? Because -2 times -1 gives you a +2. So I just made a little error there. But this is all correct. Right. And so that actually concludes our section 6.1. Were there any questions on this last example that we just did together? No, not at all. All right. So our next time we meet, well, actually, this Friday during your asynchronous day, you'll be going over section 6.2. Let me go ahead and stop our recording now.